The first attempt to reconcile Newton's corpuscular theory of light and Huygens' wave theory of light was made by Sir William Rowan Hamilton between 1828 and 1837. Hamilton was an admirer of Lagrange and wanted to bring to optics the same beauty, power, and harmony that Lagrange had imparted to mechanics. He noted the formal analogy between Hamilton's variational principle of action in mechanics, that is delta of integral L dt equals 0, or its corollary, Maupertuis's principle of least action, and Fermat's principle of minimum time, in which underlies geometrical optics. Here, c is the speed of light, v is the velocity, and n is the refractive index. The action function s, which is the time integral of the Lagrangian, satisfies p equals gradient of s, where p is the momentum, and del s by del t equals L minus pv, which is equal to minus e. For plane monochromatic waves, that is of the form e to the power ik dot r minus omega t, the wave vector k and the frequency omega equals 2 pi nu are related to the phase phi by k equals gradient of phi and del phi by del t equals minus omega. The wave vector in optics thus corresponds to the momentum in mechanics and the frequency to the energy. But these ideas did not attract much attention for nearly 100 years, since they would have implied that just as the rays of geometrical optics were replaced by waves, so too would the notion of particle trajectories have to be abandoned. And scientists were not ready to accept just such a conclusion until their hand was eventually forced by experiment. Louis de Broglie revisited these ideas nearly a century later. De Broglie began his studies preparing for a career in the civil services, obtaining his undergraduate degree in history from the University of Paris in 1910. But then he became fascinated by physics and changed fields, obtaining his licence in physical sciences from the Sorbonne in 1913. Trying to reconcile Einstein's light quantum hypothesis with the phenomena of interference and diffraction, de Broglie suggested that it would be necessary to associate with those quanta a certain element of periodicity. Building upon the formal analogy between mechanics and wave optics, de Broglie associated a fictitious wave with the motion of any particle and demonstrated that the velocity of the particle is precisely the group velocity of the associated phase wave. At every point in its trajectory, the particle follows the ray of its phase wave, which will be determined by the Fermat-Maupertuis principle. But if the particle has to pass through a slit or aperture of dimensions comparable to the wavelength of the phase wave, then the particle's path will be bent in accordance with the diffraction of the phase wave. These conclusions should apply to electrons as well. As he stated in his paper in Comptes Rendus in 1923, a stream of electrons passing through a sufficiently narrow hole should also exhibit diffraction phenomena. It is in this direction where one has to look for experimental confirmation. Relativistic mechanics goes over to Newtonian mechanics as the velocity of light goes to infinity. Similarly, wave optics reduces to geometrical optics as the wavelength goes to 0. And likewise, wave mechanics reduces to classical mechanics as the momentum goes to infinity. This led de Broglie to conclude that the wavelength is inversely proportional to the momentum through lambda equals h by p. De Broglie concluded that an electron in a stable orbit around an atom may be regarded as a standing wave, otherwise it would destroy itself by destructive interference. So the circumference must consist of an integral number of wavelengths, thus 2 pi r equals n lambda. This leads directly to Bohr's quantization condition for angular momentum, L equals pr equals nh cross, where h cross equals Planck's constant divided by 2 pi. On November 29, 1924, de Broglie presented his doctoral thesis, Recherches sur la théorie des quanta, to the Faculty of Science at the University of Paris. It was hailed by Sir Charles Darwin as truly one of the most important documents in the history of scientific research. When asked by his examiner J. Perrin whether these waves could be experimentally verified, de Broglie suggested that this should be possible by diffraction experiments of electrons with crystals. Max Born discussed de Broglie's theory with James Franck and with his student, that is Born's student, William Elsasser at Göttingen in 1924. When Elsasser suggested performing a diffraction experiment with electrons to test the existence of de Broglie's waves, Franck remarked that this would not be necessary since Davison's experiments had already established the existence of the expected effect. Clinton Joseph Davison and C.H. Kunzmann at AT&T in New York had been investigating the scattering of electrons from electrodes in vacuum since 1919. Franck and Elsasser realized that the peaks in the angular distribution of the scattered electrons could be interpreted as due to diffraction, and they exhibit features similar to those of X-ray diffraction by crystals. They thus interpreted the scattering as a diffraction process and found that the wavelength was exactly that given by the de Broglie formula lambda equals h by mv. This also provided an explanation of the Ramsauer effect, observed by Ramsauer in 1921, by Townsend and Bailey in 1922, and by R. N. Chowdhury in 1923, that for slow electrons, the scattering cross-section of rare gases decreases as if the atoms become completely transparent to the electron. George Paget Thomson, with his research student Andrew Reed in Aberdeen in May 1927, performed diffraction experiments of electrons by thin films of celluloid, showing similar patterns to those observed with X-rays. Ironsides performed similar experiments with films of copper, silver, and tin, while Seishi Kikuchi in Tokyo used mica. On November 2, 1928, Thomson announced at a meeting of the Optical Society of America in Washington, D.C., "During the last few years, we have come to recognize that there are circumstances in which it is convenient, if not necessary, to regard electrons as waves rather than as particles, and we are making more and more frequent use of such terms as diffraction, reflection, refraction, and dispersion in describing their behavior. In subsequent years, such diffraction studies have been performed not just on electrons, but with atomic and molecular beams and with neutrons." On April 30, 1897, his father, Joseph John Thomson, had announced his discovery of the electron to the Royal Institution, for which he was awarded the Nobel Prize in 1906. In his words, "For his investigations which led to the conclusion that the carriers of negative electricity are bodies, which I have called corpuscles." 40 years later, in 1937, Davison and George Paget Thomson, the son, shared the Nobel Prize for the experimental discovery of the interference phenomena in crystals irradiated by electrons. Thus, Thomson the father may be said to have won the Nobel Prize for showing that the electron is a particle, while Thomson the son won it for showing that it is a wave. Well, if there is a wave, there must be a wave equation. Enter Erwin Schrödinger. Schrödinger got his PhD from the University of Vienna in 1910. He was a great admirer of the late Ludwig Boltzmann and deeply interested in statistical mechanics and philosophy. In 1920, he accepted an associate professorship at the Technische Hochschule in Stuttgart, and after a short professorship in Breslau, moved to the University of Zurich in 1921, where he stayed until 1927 when he succeeded Max Planck in Berlin. At Zurich, Schrödinger tried to generalize de Broglie's waves to the case of bound particles. As Dirac later recalled many decades later, he finally obtained a neat solution of the problem, leading to the appearance of the energy levels as eigenvalues of a certain operator. He immediately applied his method to the electron in the hydrogen atom, duly taking into account relativistic mechanics for the motion of the electron. The results were not in agreement with observation. We now know that Schrödinger's method was quite correct, and the discrepancy was due solely to his having not taken the electron spin into account. But electron spin was unknown at that time, and Schrödinger was very disappointed and concluded that his method was not good and abandoned it. Only after some months did he return to it and then notice that if he treated the electron non-relativistically, his method gave results in agreement with the observations in the non-relativistic approximation. Schrödinger wrote up his work in a series of 4 papers published in 1926, one of the most influential contributions ever made in the history of science. In Max Born's words, of a grandeur unsurpassed in theoretical physics. Starting from the action function S, which is equal to integral L dt, which is equal to integral T minus V dt, where T and V are the kinetic and potential energies respectively, and the equations we have already introduced earlier, that is P equals, the momentum P equals gradient of S, which, as we can see from the above, is equal to root 2mt, which is equal to root 2m into E minus V. And the other equation already introduced above, del S by del T equals minus E. Schrödinger realized that S plus ds is equal to S plus V times del S minus E times dt, where V is the phase velocity with which the wave fronts of constant action travel through space. Therefore, the phase velocity is V is equal to E by modulus of del S, which is equal to E by modulus of E by square root of 2m into E minus V using the previous equation. Putting psi equals psi 0 e to the power 2 pi iet by h into the wave equation, that is the del squared psi minus 1 upon v squared del squared psi by del t squared equals 0, Schrödinger obtained the wave equation for quantum mechanics, that is del squared psi plus 8 pi squared m by h squared into E minus V psi is equal to 0. For the hydrogen atom with potential energy minus E squared by R, where R is equal to square root of x squared plus y squared plus z squared, Schrödinger obtained the Hamiltonian minus h squared by 8 pi squared m times del squared psi minus E squared by R. Stipulating that psi has to be real, single-valued, and twice continuously differentiable, Schrödinger solved the equation in spherical polar coordinates, finding that the angular part of the solution can be expressed as spherical harmonics with the discrete energy spectrum E equals 2 pi squared m e to the power 4 by n squared h squared, which is exactly as given by Bohr's formula. He also obtained the outline of what we now know today as the Rayleigh-Schrödinger perturbation theory. Schrödinger also applied his theory to the harmonic oscillator and the rigid rotor, obtaining for the harmonic oscillator the wave equation del squared psi plus 8 pi squared m by h squared into E minus half m omega squared x squared psi is equal to 0, whose eigenfunctions are e to the power minus x squared by 2 into hn by x, where hn by x are the Hermite polynomials, giving the eigenvalues En equal to n plus half h nu in accordance with Heisenberg's matrix mechanical results. In his fourth paper, Schrödinger solved the general time-dependent problem, writing psi equal to psi 0 e to the power 2 pi I t by h. He obtained the time-dependent Schrödinger equation minus h squared by 8 pi squared m into del squared psi plus v psi equal to h by 2 pi I times del psi by del t. This is now known as the time-dependent Schrödinger equation. Recognizing that this has the form of a diffusion equation with imaginary diffusion coefficient, Schrödinger relaxed his original requirement that psi needs to be real. In spite of the radically different formulations, the mathematical equivalence between matrix mechanics and wave mechanics has been established by Wolfgang Pauli and John von Neumann. Schrödinger's theory captivated the world of physics. As Max Planck said, it plays the same part in modern physics as do the equations established by Newton, Lagrange, and Hamilton in classical mechanics. In these two episodes, we have seen the birth of matrix mechanics and wave mechanics. But there was a third stream of quantum mechanics that was developed at Cambridge by Dirac. Paul Adrien Maurice Dirac graduated from the University of Bristol in 1921 with a BSc in electrical engineering, but was unable to find a job, so he continued his studies and secured a 3-year senior research fellowship at St. John's College in Cambridge, working on problems on the old quantum theory under R.H. Fowler, obtaining his PhD in 1926. In the spirit of the correspondence principle, Dirac wondered what was the quantity in classical mechanics corresponding to the commutation relation of Born and Jordan. Dirac wondered what was the quantity in classical mechanics corresponding to the commutation relation of Born and Jordan, namely PQ minus QP equals h by 2 pi I times the identity. He realized that this is the Poisson bracket, first introduced by Simeon Denis Poisson in 1809 and popularized by Jacobi in the mid-19th century. The Poisson bracket of two variables x and y is given in terms of the coordinate q and the momentum p by del x by del q times del y by del p minus del y by del q times del x by del p. Thus, Dirac identified IH cross times the Poisson bracket of x and y with the commutator of x and y in quantum mechanics. For classical variables q and p, the Poisson bracket of q and p is equal to 1, whereas the Poisson bracket of q and the Poisson bracket of p and p are equal to 0. Dirac could thus take over into quantum mechanics the whole of classical mechanics formulated in terms of Poisson brackets. For any function which is a function of p and q, the equation of motion becomes df by dt equals 2 pi by ih times fh minus hf in quantum. Dirac was able to generalize these commutation relations to systems with multiple degrees of freedom. Thus, QRQS minus QSQR equals 0, PRPS minus PSPR equals 0, but PRQS minus QSPR is equal to delta RS times h by 2 pi I, where the Kronecker delta RS is equal to 1 if R equal to S and equal to 0 if R is not equal to S. Applying the correspondence principle to the time-independent energy, which has only diagonal terms, Dirac deduced that xnm hmm minus hnn xnm is equal to IH cross times del xnm by del t, which is equal to minus h nu nm xnm, which is just Bohr's relation h nu nm equals En minus Em.